Hi. In my previous video, I did a thorough teardown of this BK Precision 1696 20 volts 10 amps programmable switching power supply I purchased off eBay. And I mentioned that there were more issues with the units than just a broken LCD itself. So obviously, in order to get this power supply back in working order, I need to fix all these issues. But before moving on to the LCD, I wanted to examine what's going on with the power supply itself and see if we can fix it. So let me remind you what was the issue I was facing. Basically, I couldn't adjust the output voltage to higher than 11 volts. And the output voltage quickly collapses if I attach a load when the output is adjusted above 8 or 9 volts. And yes, I had verified that neither the over voltage protection nor the current limiting had been engaged. Luckily, I could still use the serial communication, so I thought I'd just show you what the symptom looks like using BK Precision's SDP software. So let me show you the setup before we hop over to the computer. And as you can see, I set up the power supply here along with the output attached to this electronic load, so I can adjust the load to see the output voltage. And I temporarily hooked up the RS-232, as you can see towards the back. That one goes to the computer. The reason I need to put that on this desk here is because unfortunately the wire is not long enough. So I had to move it closer to the computer here. Now, as you can see the other end, I powered the unit up using the isolation transformer, so to make sure that it stays safe. Anyway, so now let's try to fire up the SDP software and see what we get. So now let's take a look at BK Precision's SDP software. And I have this running under a VM because I don't have a dedicated Windows machine. But anyway, it should behave the same. So now let's take a look at if it picked up. Yep, it's a COM port 1, so let's say OK. And I should be able to get my power supply here. And so right now you can see that we have the voltage set to be 5 volts and maximum current to be 9.99 amps. And output is currently off. So just to show you that we don't have the output voltage over voltage protection, I'm going to come here. And you can see that the upper limit setting is actually 20 volts. So we have a bunch of other options here, and it actually gives you some nice data logging capability. And I haven't played around yet, but nevertheless, that's not the focus here right now. So anyway, so right now you can see that the output is disabled. So now if I enable the output, you will see that actually the output measures 4.98. So this is actually the live measurement of the output. So everything works seemingly flawlessly. And I can actually change this. So if I drop it to, let's say, 3 volts, the output will change to roughly 3 volts. And if I increase this to 8 volts, the output would increase to about 8 volts. So far everything works as desired. But see, let's take a look at what happens if I increase the output voltage to above. Let's say right now do 10 volts. And it's still 10 volts. However, if I do 12 volts, and you will see that the output is only 11.0607, and the last digit will change considerably compared to the regulated output. So clearly it's somehow capped at 11 volts. So now if I further increase the output voltage, as you will see that, now I'm putting to 19 volts. And the V constant here, that's the set voltage here, it's 19 volts, but output is only 11.7. So now if I started drawing some current, let's turn on the electronic load, and I don't know what the preset current is, but it doesn't really matter. Let's turn it on. And we're drawing about 200 milliamps, and you can see that the output immediately dropped to 10.3 volts. So if I adjust the current draw, you will see that the output voltage actually is not regulated at all. So now I'm turning it down, and now I'm turning it up. So if I start drawing 1 amp or thereabout, it dropped to 9.42 volts. So clearly it doesn't have regulation towards the 10 volt output range. So now let me drop the output voltage to, let's say, 5 volts. And you will see that actually it maintains the regulation, and I can further increase the current draw, and it doesn't seem to have any problem. So we know that at least the digital portion of this power supply works flawlessly, and obviously there's something wrong with that analog portion of the digital of the switching power supply. So with that symptom in mind, let's take a look at the board to see what we can find and to see if we can identify the problem. So now we know the symptom, and let's take a look at the actual board to see what is going on. And by the way, I just found out that I can actually power this board without connecting any of the digital boards to it. So this is actually quite convenient. And when I do this, the output would just be the 11 volts. So I assume, and when it's operating correctly, this probably would be somewhere like 24, 25 volts, because the maximum output is 20 volts. Anyway, so we know that this unit has a active power factor correction unit, which is right here. It uses a MC33262 chip, and the remaining for the PWM circuitry uses this TL494. So let's start with the main side first and walk our way backwards till we find where the fault is. So I went ahead and printed out the datasheet for the MC33262 power factor controller. And as you can see, the circuit for this power factor correction circuit is very simple. And without getting too much into the detail, we can kind of see the diagram, how this thing works. So basically, instead of using a bulk capacitor, which is only discharged at the peak of your sinusoidal input waveform, we are using a high-frequency bypass capacitor here. And this is essentially a very, very small capacitor, which are one of these, or all of these capacitors right here. And then we go through this PFC circuitry, which is MC30, in this case it's 34,362, but for our case it's 33,362. It doesn't really matter. And what is important is this PFC pre-converter actually is a boost converter. It converts the input voltage to a higher voltage for the DC-DC converter at the second stage. So basically we should be able to detect the output voltage to be higher than the input voltage. So that's the first step where I'm going to try to measure. And this is important because if the PFC is not working correctly, then we won't get the correct output voltage, and then the DC-DC converter at the second stage won't get the correct input voltage, which would cause a cascading problem. So with the general operating principle in mind, we shall take a look at the voltages across these capacitors. And I did touch up the soldering on these capacitors. As you saw, the soldering job was pretty poor last time. But I was hoping that would be some of the soldering joints went wrong. So I actually went ahead and touched up all the soldering joints that I think might be the problem. But obviously did not solve the problem. So we're back here. We're going to take a look. So now let's plug this in again. And remember, every time we work with live circuit, you got to be really careful. So right now the isolation transformer is off, so I can plug this in. Oh, sorry, wrong way. We can plug this in. And so remember, our goal right now is to measure the voltages across these capacitors. These two, as you can see, are actually in series. And so we should be able to do some readouts here. So now let me turn on the power. After I turn on the power, I shouldn't, we shouldn't be touching with our bare hands on the board. So now just judging from what the PFC output is, it actually makes perfect sense. When we saw earlier the output, we could not get above 11 volts. I suspect now that's because the input of the voltage is incorrect. Because if the input is not at its rated voltage, whatever the voltage is, right now we're only at 150 volts. So clearly it doesn't matter what the PWM circuitry does. It will not be able to compensate for the significant drop of the input voltage. So to look a little bit further, actually I just touched up all these solder joints. I mean, it's not as pretty because I didn't clean it up. And I also replaced this bypass, the compensation rather, capacitor. And as the datasheet mentioned that this is a critical component, without this it won't work correctly. And it doesn't seem to do anything so far. But if you look at this MOSFET, which is responsible for chopping the input waveform for the PFC, and I would expect that we should see something on its gate. And because the pin 7, which is this one, comes with a resistor here, drives the pin 7. So when I'm looking at that, actually I didn't see any signal coming out. And I'm not sure if I want to, well, I can show you this, but anyway, I don't think it's necessary to show you that. But anyway, I can just talk it through. So it doesn't have any signal on this pin. So now I started suspecting that something actually went wrong with this PFC circuit. So let me zoom out a little bit, and let's just do a quick measurement here. So let me put this in. Okay. So let me turn on the isolation transformer again. So for the ground, it's actually referencing to the drain, which is well, it's not really the drain, but it has a current sensing resistor tied to the ground. But I can measure the drain here. And so it's roughly should be the voltage we're getting, but there's nothing here. And there's nothing. So if we look at the pin, let's see, this is which pin is that? So we have some voltages around, and so let's do some measurement on that power factor correction IC MC33262 to see if we can find anything. In the meantime, I did change this compensation capacitor, which is a 1 microfarad, and because it mentioned in the datasheet that it's a critical component, so I thought that there might be something wrong, but of course nothing's wrong. And I also touched up all the pins, and so far the symptom remains. So let's take a look at the power goes into that IC, which is pin 6 and pin 8. So 6 is ground and 8 is right here. So I'm gonna just measure that carefully. And now I turned on the power supply, and pin 6 is right here, and pin 8. So you can see, well, it's a 16.5 volts. So it's, I don't know what the actual voltage should be, but it's certainly an acceptable range. And so now another thing you can see is from this pin 7, which is the output, and it goes through this 100 ohm resistor and goes through the gate of this MOSFET, which chops the input DC voltage. So we should be able to see something on this gate. And actually I just measured earlier, but I'll show you again. There's nothing here. So again, we're on pin 6. And pin 6 is actually connected to these. So this is also ground. And let's see, this is pin, the gate. And you can see there's nothing going on here. So that makes sense, because if you don't have anything chopping this input, right, it's essentially a boost converter, and you won't see. So let's just come up with this diagram again. So if you don't chop this rapidly, turn it on and off, you will not be able to step up the voltage. So that's why the output is at the input voltage level. So far, all the symptom suggests that something's wrong with this boost converter, which is this PFC circuit. And so again, let's take a look at the output here. It's 152 volts. So clearly, we don't have the boost converter working. So now I just looked around the circuit here, and really there is nothing much to it except for this power factor correction IC. And I went ahead and changed this cap here because I was thinking this cap might be leaky and could have caused some voltage problem, but it doesn't seem to have affected anything. So this cap here is also okay, and all the resistors and capacitors and the MOSFET and the diode here, I measured everything here. Now I became more confident that this IC is the main issue. So unfortunately, I don't have any replacement IC on hand, so I went ahead and ordered quite a few of these just in case these are the issue. And these are very cheap, actually, only like 60 cents per chip. So I ordered 5 of them, and they should arrive in a couple of days. So in the meantime, I can't do anything about it, and once the IC arrives, we should be able to verify whether that was indeed the problem. Okay, now it's a couple of days later, and my supply arrived. I not only ordered this MC33262, I also ordered a couple of TL494, just in case that was the case. Actually, the packaging came really nice, and I only ordered 2 of them, but they put it in a longer tube than necessary. So this is a TL494, and this one is really shocking. It's actually a very long tube coming in, but I actually only ordered 5 of them. At least I think it's 5 of them. Take this out. Yep. So as you can see, the rest of the tube is just empty. But here are the stuff I ordered. So let me replace one of these, and we will fire it back up. So during the past couple of days, I've been playing around and trying to see which is exactly the component that caused the problem we were seeing for the output voltage not to be able to rise to above 11 volts. And my first theory was there's something wrong with the PFC circuit, but after replacing that, it didn't seem to have made any difference. So now I'm back to the drawing board, basically again trying to determine what else could be wrong. Now, the PFC definitely has some issues because we know that the output should be higher than the 150 volts that we measured. So, but that's probably not the only issue. But anyway, so I actually ordered a couple more parts, and while waiting for that to arrive, and I'm going to take a break from trying to figure out the power supplies issue, but going to be concentrating on reverse engineering the LCD protocol, so that once we fix the unit, we can use our own LCD and using the signal to drive it. So while we are waiting for the hardware side of the board to be sorted out, as I mentioned earlier, I did change a couple of components, and apparently it didn't solve the problem. So I needed to dig a little deeper. And before I figured that out, I thought we could do something in parallel. That is to reverse engineer the protocol used to display data onto the LCD. Since that is critical because we don't have the backup LCD, so I have to use a different LCD, and by understanding what data is sent to the LCD, makes it possible to utilize a different LCD for the display. So for that, I hooked the LCD driver up to a signal analyzer, to a logical analyzer, and I have set the protocol to SPI. And for the SPI protocol, and this is strictly speaking not a SPI protocol, and as you will see a little bit later, but nevertheless, it could be used to decode the actual data. So I will just show you briefly what the setting is. Basically, the enable line is actually different. Enable line here is set to be enabled when the active is high, whereas the standard enable is for a low voltage. So anyway, so let's get started to see if we can capture any data. So now, by the way, to do this, I had to set the power supply up on using an isolation transformer, because I don't want to accidentally blow up either the computer or the analyzer or the power supply, for that matter. Right now, to make the things a little more complicated, is because we cannot read the actual readings from the LCD. So I had to use this SDP software to do the actual trick to set the power supply. So due to the setup, it's a little bit of noisy, and while I have the recording going here, I actually tried a couple of times. I noticed there's some interference on the digital line, but I'll explain this later. When later on, I will redo the traces, and hopefully we'll make them cleaner. So anyway, so let's take a look at what we get when we start the trace. So as you can see here, we have some decoded data here because we set to SPI protocol, and it automatically decodes. Now, the first thing you see is actually these 120 hertz line across the different, the entire spectrum actually. So that's actually not supposed to be there. Those are just some interference from the power line, and again, due to the cabling. So we should ignore those, and actually if we take the measurement without those things, these errors would not occur. But anyway, regardless of what disregard those spikes, and we can see there's some data in the middle, and the frame here is about 10 hertz, so it's roughly 10 times per second. So if we zoom into one of these, you will see that it actually is a pretty neat data package. And so by looking at this, again, this particular peak should not be here. And that's because we see this again is 120 hertz, so that's actually the power line interference. But when we look at this, you will see that if you read the datasheet for the LCD driver, you will see that the first frame here, which is represented via this pulse for the first CE in the chip enable, and corresponding to this mode select. So what happened is here we have 4 bits sent over, and so those are just to set up the communication for different channels. And for this particular LCD, all these first 4 bits for the data package are the same, so we would ignore here. Actually, this analyzer software actually simply just because it's half a byte, it simply didn't decode this. So actually, that's to our advantage, because we wanted to see what is happening after the mode pulled low. So that would be our data package sent over to the LCD. So as you can see here, we have actually I counted earlier, it's all here. So there are 25 bytes sent over to the LCD. And so my plan is to adjust the power supply via this software here, and at each step I'm going to record what I see from the recorded package, the packets. So when I'm done, we should get a picture of the data being transmitted. So for example, right now if I set the voltage to 10 volts. By the way, before I set it, we want to come here and take a look at the so it's a BEBF, something like you can see here. So let's change to 10 to see what changes up here. So now we change it to 10. Okay, and so now we should let me minimize this one. We'll start trace again. So, and right now you probably can't tell which one changed. But what I'm going to do is I'm going to hang on. Let's take a look here again. So again, these would be different sets of data. So basically, my plan is to do certain variations. For example, we need to be a little bit strategic about this. I would first adjust the voltage with the output off and little by little and see what are the data patterns. And then I would fix the voltage and adjust the current setting little by little and see what the pattern is. Finally, I would enable the output and set the voltage and adjust the current. So every step I will do is going to be individually so that I can see at each step what bit pattern changes corresponding to what actions I took. So anyway, so here basically now I'm just going to go offline and capture some of the packages, and I'll be right back. Okay, so I spent a lot of time, basically, as I mentioned earlier, trying to vary each of these variables independently to one another and captured the output data. And what I have highlighted here, as you will see, is the actual bits that, well, these are bytes that are changed during each variation of the settings here. So for instance, here you will see that VO is the output measured voltage, and IO is the output measured output current. WO is the displayed wattage, and VS is the set voltage, IS is the set current, and on is basically indicating whether or not the output is on. And the remote is, well, here is always enabled. So, and I also took a screenshot from the software. Basically, you can see the actual display here. So the plan here is basically, as you can see, at first I did 1 volt, setting the output 1 volt, and the current is set to 1 amp. And then I varied to 1.1, 1.2, 3, 4, so forth, until I hit 2. Then basically now I just do the amp all the way to 20. So this way I should be able to capture all the information I need. So, and I actually went ahead and did some decoding, and it's not actually that straightforward. So as it turned out, so to do the decoding, you also have some tricks. So for instance, right now we have this, let's say 1.8 and 1.0, which is 1. So these two columns. So when you see these two, what is different between these two is actually that single segment inside the 8. So that is the difference between 8 and 0. So we should be able to find that difference in our data here. So as you can clearly see, that's the difference between the 7 and 7D. So basically, I'm going through the exercise, and so I came up with what actually the 7-segment digit representation of each bit is. So here, let me zoom it out. So here it is. So basically, the first bit, which is so I'm starting with the highest is your 7th bit. The lowest is your 0. So basically, from 0 here is used as your decimal dot. And so this is the first bit, represent this segment of the 7-segment display, second, third, fourth, fifth, sixth, and 7th. So these are actually not a standard 7-segment display, but nevertheless it serves a purpose because everything is inside the software and they can do pretty much whatever they want to do. So in this case, this is how each digit is encoded. And again, if the lower bit is set, that's a decimal place. So based on this, let's take a look at some of the data we captured here, B6, 7, and 8. And as you can see, we have some captured data. So by the way, so here is what the actual representation would be if I write out the 0 through 9. So I did that ahead of time so I can basically, kind of quickly recognize what each is. So so have that in mind. Let's take a look at this 0.7, right? So 0.7 is basically your 1 because the 7 is 0, 1, 1, 0. for those who are not very comfortable with a hexadecimal and binary calculations, I actually have this calculator. Clear all. I actually wrote this calculator a long time ago, and you can actually find a copy to download from a website, and they can either run on Linux or Windows, so it's quite convenient. But anyway, so the point is, if you are not familiar with the binary representation, you can kind of you can just put it in. It automatically, for example, the 2 here, and it automatically shows you all the translation, including the bitmap here. So that is makes it a little bit easier. So anyway, so the 7 here is, let's just hexadecimal 7, and you will see that's a 110. So what is 110 here? Well, you will see that we have 1, right? So that's the 1. So basically, that's your digital 1. And the BE, let's see what is BE. BE is basically 101 and 1110. So this is actually a 0. So this is our basically 1.0. And similarly, the 6 is a 1. So the 6 here, so let's put 6. So you can see it's 110. So that's your 1.1. So okay, so 1.1. And then 1.2, 1.3, so on and so forth. And finally, when you reach out to the tens of volts, the B6 start kicking in. Before that, B6 is all zeros. So that's what the first digit comes out. Well, sorry, that's what the set voltage coming from. So from this 3 bits. And then we can keep working our way up. So now we have the set current. So for the set current, again, you can see that there are 4 bits that, 4 bytes that are at play here. Let's take a look at what we have as a 0.01. So this turns out to be a little bit more difficult, as the digits actually are not exactly defined over a byte boundary, but rather is actually defined over the nibble boundary. So I had a little bit of write-up of this on my website, and for those who are interested, you can go and check it out, how these map back to the actual digits. But to keep the story short, is that here are the representations of 0.1 through 9.99. So we can map the current setting to this 4 bytes. And so now we move on to when we turn on the output, right? So once we have the output enabled, we can actually do the similar exercise to figure out where the digits are and how the digits are stored. And this is a little bit of tricky again, because you now, even though you set a certain voltage, and the actual displayed voltage might be slightly different than what is being set, because this is actually the measured output. And also when you have the and you notice here, so this clearly shows the problem of this power supply I have. The output setting is 12 and actual display is 1114. So, and then after I did this, I went ahead with setting a fixed output voltage with some current changes using an electronic load, and captured data again. So all these actually make perfect sense. It's a little bit of complicated to fully explain here on the in this video, but if you are interested, please go to my website and check out how each of these data element is represented. So I think this pretty much captures the entire protocol. And so if we build a circuitry that can interpret this serial protocol, and then we should be able to totally bypass the LCD driver and drive our own digital display for whatever display we choose. So I hope you liked the video and learned something new. If you did enjoy the video, please give it a big thumbs up, and do remember to subscribe, share, and it will certainly help this channel quite a bit. And I will catch up with you next time.